Hi, everybody. I appreciate you listening, and thank you for the introduction, Rob, and Mr. Inglis. That was amazing. Two mechanical engineers going back to back talking about ICS cybersecurity. So representing. I'm Gus Serino. I work for Dragos. In case you didn't realize, I'm part of the OT Watch team. If you don't know what that team is, we are an add-on service to people who buy our platform. So we do the monitoring of the security stuff within the environment and do threat hunting and things like that. And so that's currently honored to be doing that. And my talk on detection in depth, I'm going to be talking about threat detection like over a couple different aspects, looking at critical process parameters, using traditional ICS stuff to get good situational awareness on what's going on with the control system just in general, and also to use that for cybersecurity awareness. And then along the way, I'm going to talk about general traditional network security monitoring, continuous security monitoring. So prior to joining Dragos, as Rob mentioned, I spent about 15 years working for a water wastewater utility up in Massachusetts on the SCADA team. And there are several of us who had that dual role of, doing traditional automation stuff as well as securing the ICS OT stuff. And so we spent a lot of time thinking about scenarios we needed to defend against and how we were going to deal with that. And sort of one of the worst case scenarios that we all thought about was the situation where an adversary gains access to the system, undetected obviously, and uses the control system to manipulate the process, masking what they're doing and causing harm to the process. And so how we try to consider how we could defend against that and detect that. And we felt pretty good about our the measures we were taking on the protective side, the firewalls, the hardening, the patching, all that kind of stuff. Although we all know that only gets you so far, that stuff gets bypassed, and we were not super confident about how we were going to detect when this occurs. And so, we spent a lot of time trying to figure out how we were going to do that. And so out of a project that had nothing to do with cybersecurity came a concept that we could leverage our control system to help us, existing pieces of equipment within our control system to help us understand when this might be occurring, when somebody might be manipulating the process. This screen up here is an HMI graphic, and out of a workshop working on ISA 101 high performance graphics, we came up with the idea. So if you're not familiar with what this ISA 101 stuff is, it was basically a study that looked at how HMI graphics were being developed. On the left-hand side of the screen, is how they typically are, with lots of colors, things moving, flashing, lots of visual information. And they determined that scenario didn't actually help operators to determine when the process was in a bad state, when there was a problem. And so the trend is to clean that up and go to the right side, which is a much more subdued graphic with only those critical parameters that you really need to determine if the process is healthy. And so the workshop you go through to kind of get from the left to the right, you get the operations people, the engineering folks, the process control folks, the SCADA folks, managers, and you kind of figure out what are those key process parameters that we really worry about to tell us what the health of the process is. When something's going wrong, what signals are you going to look at to figure out if we're in real trouble or if we're okay? And so that was kind of the light bulb that said, all right, so now we've taken thousands of signals and boiled it down to hundreds of signals that are the ones that we really care about. And so we were fortunate. We had existing systems out there where we were doing either revenue metering or just backup systems where these critical parameters were tied to an alternate means of monitoring them. And so we had to do some expansion and some reconfiguration to get there. But the idea was this. All right, so this is a typical SCADA system, right? So at the bottom, we see a pressure instrument that is in a 4 to 20 milliamp loop to the PLC, which then communicates over the network to the HMI to display the whole process to the operator. From the HMI, everybody knows this probably, right? So the HMI then goes to the historian for long-term analysis and things like that. On the other side, in that same 4 to 20 milliamp loop, we send that pressure signal to a data logger, which goes up on its own telemetry to a data logger server, and then into the historian. From there, we can compare those two signals with the historian and figure out if what the pressure indication is through the traditional SCADA route is equal to the same one coming over that alternate path, and figure out if there's a discrepancy there. I mean, this doesn't work for everything. You're not scalable. You're not going to do it for everything. But for those signals that you really want to care about and want to know if something's awry, it made sense. And we were fortunate that we had a lot of this infrastructure in place to use it that way. This diagram is the field side of that. So on the left-hand side, we have a traditional 4 to 20 milliamp loop. On the left there, you see the 24 power supply, sending DC current through the pressure transmitter up to the PLC, then through the signal isolator, which I'll talk about in a second, through a digital panel meter, which is basically a local indication at the site of that value, and then completing the loop back to the DC power supply. And so that's the primary 4 to 20 milliamp loop. The signal isolator, which is essentially, you see it, the green thing on the lower right there, comes in all shapes and sizes, but it basically takes a copy of that 4 to 20 milliamp signal and sends it to the data logger, like I mentioned, and then that has its own set of telemetry. It could be cell, could be plain old telephone line, whatever it is, to communicate that back. This is sort of the data center architecture of this whole thing. Similar drawing at the bottom. You see the independent path to the data logger server in the enterprise network. You see the normal path of SCADA telemetry up through the HMI, and then both land in the historian, and then a separate application sitting on top of that, comparing those two values to basically alert on if they're different. This is the kind of the crux of how we could use what we already had. We didn't need technology, we didn't need cybersecurity knowledge, just a way to validate those most important signals to make sure that they were actually reading what the SCADA system said they were reading. So that's the idea. I'm done now. But I just want to pivot a little bit, change directions, and talk about this in the framework of the ICS kill chain, and with a sort of conceptual attack scenario. In this attack scenario, it's basically adversary gains access to the environment, similar to what I talked about in the beginning, gains access to an HMI. Once they recognize that it's an HMI and start to do stuff with SCADA stuff, that's when we sort of transition from stage 1 to ICS kill chain stage 2. And then I want to highlight how much can be done with an HMI, not leveraging changing code in a PLC or anything like that to abuse the process, and how important HMAs are as a crown jewel and something that need a little bit extra attention and scrutiny in terms of security. So to do that, I'm going to step through the different phases of the attack. So here, we're at ICS kill chain stage 1, so still enterprise level at ACT. This is where the adversary gains access into the environment and eventually pivots to an HMI, which is just a Windows box at this point, nothing ICS related at this point, right? So I am going to talk about the Pulse Secure VPN vulnerability and exploit as the avenue in. And this is something that was being abused a lot a couple of years ago. There were definitely a few ICS organizations that were compromised this way. In fact, I spent some time talking with Vern McClandish, who works for Dragos on the IR team, who's awesome. And he talked about responding to one of these incidents and gave me some insights on this attack. So it's a little bit out of scope for the talk, but I think this is really interesting, the Pulse Secure VPN part. So I want to just talk about that for a second, because this victim, they were fully patched with this VPN, with their Pulse Secure VPN device. They had a firewall in front of it that blocked everything except 443 coming in, because you have to have that. And then they had multi-factor turned on in the VPN device. And this exploit, which used 2 0 days, basically allowed the adversary to bypass the multi-factor and get in with legitimate account credentials. And so I think it's interesting to talk about how that happened. So the first 0 day was basically the attacker was able to inject code into the web server PHP file of the VPN device that would run the code and give them bash command line access on the device. Then the second 0 day elevated the privilege of that account to root level. So they had administrative privileges on the VPN box, which allowed them to install a password scraper and gain legitimate account credentials into the environment. They could monitor sessions. The adversary was smart. They only did their stuff when the normal users were doing their business. And they were in there for literally months before an outside entity notified the victim that this was going on. And so, so there was a lot here. And so it's pretty incredible kind of scenario there. And I just wanted to highlight that because, you know, this is the importance of protection and detection and response, a balanced approach. If you think you're good with multi-factor and a VPN, but you're not doing monitoring and you're not ready to respond, you got to step up and do a balanced approach across there. So, so I want to talk a little bit about detection, right? So I just added some IDS, some network sensors, and some host-based detection, right? So we think about how to detect this. And I just want to quickly go through some of these things. Certainly looking at logs, looking for configuration changes within devices is really important. You have to turn on the logging, turn on the web shell logging, or the web logging, turn on configuration change logging and look at them because it's important. You know, you may not have detections pre-built for all this stuff. That's what threat hunting is all about. It's going and looking for the adversary before the incident happens. So these are things that we can do and we do and we need to do to kind of identify this stuff before, you know, take advantage of the long dwell times that occur here. Other things to look at for detection are behavioral changes. Do you see IP addresses from locations that don't make sense? Do you see geo IP velocity is a concept where, you know, you have somebody connecting in from one location, maybe, you know, local to your site, and then in a very short amount of time later, connecting in from somewhere else. And so is that travel time, does that make sense? Is that something to look at? Another thing to look at is time of day access. Do users have patterns on when they're connecting in and doing their work? And is there access outside that window? In this case, the adversary was pretty smart and kind of avoided that, but that's not always the case. And so it's something to think about. Another thing to look at too is changes in user behavior. Do you have a user who's VPNing in and going to like accounting systems or billing systems or something else and going or not going to the HMI, and then all of a sudden you see them logging into the HMI? Those are the kinds of things that can help tip off something malicious going on. There's a bunch here that I want to talk about or that we can do to look for this stuff. I can't talk about everything, obviously, so I'm going to move on quick. I do want to highlight one really cool thing that Vern and the victim did when they were looking at this is, you know, they took the authentication logs within the VPN device, and they basically said every, you know, user that logged in, here's their IP address in the authentication log. They went through the multi-factor steps, take those and take them out of the equation. And now we're going to look at every IP address that's connecting through here that isn't in that authentication log. And they built a detection in Splunk to basically detect this until patches were deployed and, you know, and look for multi-factor authentication bypass. And I think that was a really cool approach to dealing with this problem. So I just wanted to highlight that and thank Vern for spending the time telling me some of the insights from this response. Moving down into the HMI, right? So they get in, they get legitimate credentials, they pivot into the HMI. How can we find something there, right? And so again, you know, we're looking for new processes executing on that HMI. We're looking for new user connections, normal behavior, scanning activity, things like authentication failures followed by success indicating brute force, file transfers to external addresses. All these kinds of things are all indicators of something going on. And so I just wanted to quickly talk about traditional ways of detecting this attack as I move through. So the next phase of the attack, which is basically the adversary has gained access to the HMI. Now they realize what they're doing. They take those HMI files and they migrate them out of the environment. So this is where we pivot from stage 1 ICS kill chain to stage 2. So now there's some ICS knowledge and interest going on. One of the points of what I wanted to present is how important HMIs are and how they alone give enough tools to an adversary to cause harm in a process. And so some people here may not be from the ICS side of the world. And so I wanted to kind of quickly talk about how an HMI is sort of built. And so HMI, right, we have the graphical representation of the process. We have alarms that kind of tell you when things are awry and control actions to turn things on, turn them off, put them in auto, manual, change set points. All that it functions with a database. So there's tags built into all those things in those graphics and alarms and et cetera. Within that HMI database, there are things like alarms, set points, and engineering units and all this other kind of stuff. But one really important thing in there is the IO address for the memory location in the PLC where that piece of data lives. And so that is like the crux of what I'm going to talk about next on why, you know, just having data HMI access is enough in a lot of cases. And then this other piece on the right there, the scripting engines and schedulers, these all are features on a HMI that you can do really cool things. They can also be used for abuse as well. So how do we detect this? You know, we're looking for connections to external IP addresses, file transfers to external IP addresses. Is that normal for your HMI to be doing that? Looking for changes in configuration files, things like HMI application logs, right? So that is a really good source of information to include in your collection management framework if you have one. Because when you're doing an investigation, HMI application logs have indications when users log in, when set points get changed, when configurations are changed, all that kind of stuff is in there. It's really a good source of information. And then finally, service restart. So when configurations change, as you know, oftentimes you need to restart the service for that to be recognized. Sometimes that's part of normal maintenance, but if you're looking at that, maybe you can identify that, no, this wasn't normal maintenance, something's up here, we need to take a look. So just some ideas for detection of this phase. This part here, which is where basically the adversary is sort of developing their attack, and this is conceptual, but certainly realistic. Within, you know, these are two database blocks for the HMI database. I have highlighted sort of the PLC IO address down there, and this is an older style, right? So we're looking at F12.0 there, which is a floating point in a table, a data table, and you know, word 0, and that is basically where this pressure value lives within the PLC. Well, it's trivial to change that address, and now the HMI is no longer looking at the right location. And of course, doing it in one place isn't going to do it. But you know, when there's multiple teams of adversaries who know what they're doing, you have somebody gaining access and then somebody who knows ICS, it's doable to figure out how many things I need to change to be able to manipulate this process and have it not be observable to an operator. So that's the idea. I just wanted to kind of quickly spell that out. And obviously, in this case, this is happening in an adversary's development environment, so you're not going to detect it. They don't need to do it that way. If they have this level of access, they can just do it right on the box. Maybe you can see it, maybe you can't. In fact, they could probably just open up a view node at their infrastructure and come on like another operator, to be totally honest, with this level of access. So this is why it's so important with remote access to secure it as best you can and monitor it, because the don't necessarily always realize the capabilities that are available with it. And then, so those HMI files that were compromised are coming back in. Same sort of stuff for detection here. So I'm just gonna go past this, right? So they've taken the files out, they figured out what they need to do to mask their attack and modify what they need to. They put them back in, and then they execute their attack, right? And so this is a really simple version of a water system. You see on the right, a storage tank. The level in that tank is measured by that pressure instrument at the bottom. That instrument reports the level to the tank. HMI is polling that. We see the PLC here in the pump station that's controlling the pumps that are filling that tank up. Those PLCs are probably talking to each other as well as the HMI. The thing about this is that's the same infrastructure and the same data and the same stuff that's going over those network connections between the HMI and the PLC. So there's very little that can be done in terms of detection here to figure out, you know, they've gotten all the way through compromises HMI. It's hard to detect with traditional tools this stage. That's why this thing is here. So here we have that data logger again, tied to the pressure instrument, sending its own telemetry back to the data logger server, and the whole thing that I talked about here, where we have, you know, an application sitting over the historian that's comparing those two values, says, hey, I see a discrepancy, sends an alert, SMS, email to a separate audience, maybe sends it to the operators, but also to supervisors, engineers, whoever else is going to be looking at this and say, hey, I think we have an issue. Let's go take a look. And that is just an important level of situational awareness for those signals that we really care about. So I just want to quickly go through a couple of response scenarios with or without that, or without and then with that in place, just to kind of show you, how this may help, right? So here we have on the left-hand side a typical graph of like tank level going throughout the day as outlet pressure, and normally a water tank in this case will be cycled throughout the day to keep the water fresh, and so it gets filled before the morning high demand period, drains down throughout the course of the day, and gets filled up again with those pumps. In this case, right, so my hypothetical scenario, adversary knows when to do this, right? So they stop the pumping, and the operator continues to see the green line going up, so everything looks fine on the HMI. At the same time, the actual real tank level, which is the red line, is continuing to draw down due to demand. And then in the morning here, when people are businesses are opening, people are getting up, maybe that tank level is low. And now we have real issues to the consumer. We have firefighting problems. You're starting to get phone calls. This is not where you want to be, where your users are telling you there's a problem with the service you're delivering. Think about large water systems. It's not like you're walking around a plant to figure out that things are awry. These are distributed all over large geographies. And you just may not have awareness that this tank isn't in the state that you think it's in. And so this is dealing with now a cyber attack and a physical problem at the same time, as opposed to this scenario with that out of band monitoring in place. When the pumps stop, as soon as the deviation of a certain threshold comes up, now you get that differential between what the data logger is saying and what the SCADA system is telling you. They can send an alert and say, hey, we better go check this out. Sure enough, there's a problem. Let's kick in our emergency operating procedures, start those pumps, start filling the tank. And now we're dealing with just a cyber problem, which is enough, right? And not dealing with a physical problem at the same time. So I don't know. My hope here is that, just present an idea of using what you have, not necessarily cybersecurity technology, to help build a resilient system. Situational awareness, it's not the end all be all, obviously, to everything, but it's a good tool to have in the tool belt. Also, it serves as a backup monitoring solution, right? So if your telemetry goes down or your PLC goes down, you can at least monitor those critical signals and see, what the state of the process is while you're repairing and responding to events. So I don't know, this is something that we implemented. I thought it was really, useful. Hopefully somebody else finds it useful, and you can use it. I just want to give a couple of thank yous to people who helped me with this. Was Vern, of course, Vern McClandish, Alexi Gaida, and Aaron Boyd. All were really cool and helpful in terms of some of the things that are outside my sort of my OT ICS experience. So appreciate that.